Okay, so moving along into chapter 9, we've discussed reaction rates, so now it's time obviously for chemical equilibrium. Now, chemical equilibrium is not a simple topic, so we're going to have a multiple section approach to this. So in this first one, we're just going to generically define chemical equilibrium. We're going to link it back to reaction rates, and hopefully, if you haven't seen this before, it will start to fall into place and make a lot of sense. If you've seen it before and never understood it, hopefully we'll change that. If you are still having trouble after this lecture, then certainly reach out to me for some guidance. Up until this part of the course, we've probably led you to believe that reactions happen in one way. We take our reactants, they combine and make products, or they decompose into products, or whatever the case may be. And that's not always the case. Oftentimes we have what are known as reversible reactions. So a reversible reaction can go in both the forward and reverse directions as long as you have all the reactants and products present. So there's really two rates going on. There's the rate of the forward reaction, which is sort of the rate we've always been following and the reaction we've always been following. And then we also have to consider the rate at which the reverse reaction occurs. So when molecules first begin to react, of course, the forward reaction is the one that is much faster. We start in most cases with only reactant. So we have no product to begin with, so we can't have the reverse reaction happen. So as that forward reaction starts to occur, it's fast because there's lots of reactant molecules around, the reverse reaction initially really can't go backward because there's not enough products, and then slowly we form more products and it starts to become appreciable. So that's what we're really considering, is as those reactants get consumed over time, so we have less and less reactants, as we're making more and more products, those accumulate, and we get to a situation where the rate of the forward reaction decreases, the rate of the reverse reaction increases, and ultimately at some point in most reactions that are reversible, we'll achieve an equilibrium where the forward reaction rate and the reverse reaction rate are indeed equal. So here we see a graph with that same process represented. So we have initially the forward reaction, so those red dashes. Initially it's quite fast because we have essentially all reactant, no product. The only way we can go is the forward direction. There's lots of reactant particles around, so you get lots of collisions and therefore a great number of successful collisions. And as long as you have sufficient energy, the reaction proceeds with quite a remarkable rate. If we look at the reverse reaction, initially there's almost no products, essentially zero in the way of products, so that reaction can't go to any appreciable extent. But as more products are formed and as more reactants react, we get a situation known as equilibrium, where the rate of the forward reaction has slowed, the rate of the reverse reaction has increased, and they meet at this equal rate time. So the only thing that has to be equal at equilibrium is the rate of the forward and the rate of the reverse reaction. We can still have more reactants or more products depending on the position of equilibrium, as it's called, but the rates have to be equal to achieve equilibrium. And equilibrium is a dynamic process. We have reactions going forward and reverse at the same rate, so there's no overall change, but there is indeed a change going on. Those forward reactions are still proceeding, the reverse reactions are still proceeding. They just cancel each other out, so that at the macro scale, at our naked eye level, it doesn't look like there's any chemistry happening. But indeed, we have both forward and reverse reactions occurring. It's just that they are occurring at the same rates, and therefore we see no net change. So let's consider a certain reaction. So if we have sulfur dioxide, SO2, and oxygen gas present initially, as they collide, the forward reaction will begin. So we have only the reactants, we have no product gas yet, so those reactant particles will collide with one another, and if they happen to achieve the right orientation with sufficient energy, we'll get successful collisions. Most of our collisions will be unsuccessful, but again, as long as we get some successful collisions, we'll get some noticeable reaction rate. Once we start to form those SO3 molecules from the successful collisions of SO2 and O2 molecules, those SO3 molecules can also collide with each other and decompose back into our starting materials. So that's what we call a reversible reaction. In the top reaction, that's how we've been representing reactions up until now, and we show just a single arrow. In the bottom reaction, where we acknowledge that there's both a forward reaction and a reverse reaction, I hope you notice that there's a double-edged arrow, and actually that's not the preferred one. The preferred one has just an up arrowhead on the forward reaction arrow and a down arrowhead on the reverse reaction arrow. So be careful. The text doesn't represent it justly, but that's what we have. Okay, so there you have it, reversible reactions shown by two arrows, a forward and reverse arrow. So after that process has equilibrated, once we come to equilibrium, what that means is we still have a forward and a reverse reaction, but the rate of the forward reaction becomes equal to the rate of the reverse reaction. So there's no net change over time. Everything looks like it's static, but in reality it's dynamic. So the forward and reverse reactions both continue, but they continue at equal rates. So as much as we're forming of product in the forward direction, we're using up that same amount of product in the reverse direction, so we have an equal rate. We might end up having more or less concentration-wise, right? So we might still be heavy in reactant or heavy in product at equilibrium. What won't happen is we won't get changes in the concentration. So we don't have to be equal concentrations. That's a big misconception. That's almost never true at equilibrium. You almost never have equal concentrations of reactants and products. What you have is equal rates of forward and reverse reactions. So just be careful about that. Most reactions settle into favoring either reactants or products so that you have a concentration of reactants, for instance, that is greater at equilibrium than products, or vice versa. It's very rare that you would have both the equal rates, which are necessary for equilibrium, and equal concentrations, which is not necessary for equilibrium. All right, if we consider another reaction, let's consider the reaction of hydrogen gas and iodine gas to form HI gas. All right, and because of their diatomics H2 and I2, we need to form 2 moles of HI for every mole of H2 and I2 that react. So if we have that at equilibrium, the forward and reverse reaction rates occur at the same rate and are shown together using that double-sided arrow. So the forward reaction is the reaction we've always shown. The reverse reaction is the products are now the reactants and the reactants are now the products. And so we could show either form with the double arrows indicates that it's a reversible reaction. So we don't have to show both forward and reverse directions. If we include the double arrows, then it's understood that this reaction can go in the forward or reverse direction. And truthfully, most reactions are at least somewhat reversible. They may favor the products or favor the reactants greatly, but most reactions do have at least some reversibility to them. Okay, if we look at another particle diagram where we're looking actually following the H2 and I2 particles in the HI that we produce, we see at time 0, we have only H2 and I2. We have just reactant particles. They haven't been allowed to react yet. At B, at 1 hour, now we've made some of the product. We have a couple of those HI molecules, but we still have H2 and I2 molecules present. At time C, now we see we've made even more of the HI, and we have even less of the H2 and I2 present. And then finally, by the time we get to D and E even, so after 3 hours or 24 hours, it doesn't matter because the products stay. So initially we had 0 products. In 1 hour, we formed 2 moles of products according to this particle diagram. You can see the 2 HI molecules, the big purple with the little white on it. Then by the 3rd position there, hour 2, we've got 4 of the HI particles. And then finally, as we look at the D, we end up with 6 HI and just 1 mole of the H2 and 1 mole of the I2 left over. And that could go on forever. At 24 hours in E, at 24 days, if we could map that, we would see we still have the H2 and the I2. There's still some that could react that doesn't, because while that's reacting in the forward direction, we have at the exact same rate HI decomposing in the reverse direction. So that's why we end up still having some reactant and products at our final equilibrium, because we've achieved equal rates of forward and reverse reactions. The rate at which we're consuming H2 and I2 is exactly equal to the rate at which the I2, or the HI rather, are reforming H2 and I2 once we achieve equilibrium. Okay, so hopefully that's clear to you from this picture and from our discussion so far, but please do follow up if you have questions. All right, so if you don't think you have questions, I have a question for you, and that is to write the forward and reverse reactions for the following scheme. So CH4 gas, methane gas, plus 2 H2S gas, 2 hydrogen sulfides, are in equilibrium or proceed in the forward and reverse reaction to make carbon disulfide, CS2 gas, and 4 moles of hydrogen gas, diatomic hydrogen. So go ahead and write the forward and reverse reactions for this. Pause the video here if you need to. And then once you've got those set, go ahead and see how you did by starting the video back up. Okay, so here we have it. It was written with the forward reaction, but because of the double arrows, we'll have to break it up. So the forward reaction would be the methane gas, 1 mole of methane gas plus 2 moles of hydrogen sulfide gas reacts to form, or yields is oftentimes how that arrow is interpreted, 1 mole of carbon disulfide gas plus 4 moles of hydrogen gas. So there we have it. That's our forward reaction. The reverse reaction would be to show the reactants as products and products as reactants. So more normally you'd see CS2 gas, 1 mole plus 4 moles of H2 gas yields 1 mole of methane, CH4 gas, plus 2 moles of hydrogen sulfide. Or we could also just show the forward reaction with the arrow going the other way, which is why we do the double-sided arrows. But again, if you wanted to be more traditional about things, if you have just one arrow, then you should really have reactants on left going to products on right. We shouldn't show it as that lowercase, but that hopefully that bottom one gets you thinking about why we put the double arrows in for equilibrium. All right, let's end this introduction to chemical equilibrium with a learning check. So go ahead and complete using the terms equal, not equal, forward, reverse, changes, or does not change as appropriate in these blanks. So for instance, reactants form products in the blank reaction. So go ahead and see maybe there's a couple that would seem logical and one that would seem best. So go ahead and fill in those blanks in those 5 sentences with those terms equal, not equal, forward, reverse, changes, or does not change to fill in those blanks. Start the video back up once you've done that, but go ahead and pause it here to complete your work. Okay, and here we have it. So hopefully you arrived at these same responses. So number 1, reactants form products in the forward reaction, right? That's what we're used to. That's what we've been talking about since we've addressed the idea of chemical reactions a while back. Number 2, at equilibrium, the reactant concentration does not change. We could have easily said the product concentration there as well. So that's what chemical equilibrium is. It's a situation where the concentrations no longer change because the rates of forward and reverse reactions are equal. But again, it doesn't mean all the concentrations are equal. It just means reactant and product concentrations no longer change because the rate at which the reactants are being consumed equals the rate at which the products are reforming reactants. Number 3, when products form reactants, it is the reverse reaction, right? We ordinarily talk about reactants forming products. That would be the forward direction. So when products form reactants, it is the reverse reaction. Number 4, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, right? It's the rates that are equal, not necessarily concentrations. Be careful. Equilibrium is all about equal rates of forward and reverse reactions. Finally, in number 5, we have if the forward reaction is faster than the reverse reaction, the amount of products change. Again, we don't have a situation where we have achieved equal rates yet, so we are not at equilibrium. So we are having concentration changes because we have a faster forward reaction than the reverse reaction. So if it's faster, then ultimately the amount of products should be increasing since we're making product faster than we're using product. So hopefully those went well for you, and this is a more comfortable topic. We'll be continuing our discussion of equilibrium into the other sections of the chapter, so if it's not entirely clear, you may want to just hold off and see if things get clarified, but certainly if you're really lost and need help, don't hesitate to reach out to me. Otherwise, I'll see you in the next section.